Okay, so let's wrap up this topic, the actor critique introduction topic. What did we learn? So previously we saw the reinforce approach, which in any case we need to get some estimation of the, right, using the policy gradient theorem, we need to get some estimation of how good a specific action was in a specific state. The basic approach simply uses the observed return after performing the specific action and at the specific state and seeing the return that we observed after that time step. That's the basic reinforce algorithm. Then we saw something else, but now I'm presenting it in a different way. We also saw a Q actor critique, where instead of the capital G, we replace it with an approximation of the expected G, right? So not a single sample observation, but we're trying to approximate the expected value of G with a Q network, with the Q approximator. So we can replace G with a Q value, and then we have a Q actor critique. In any case, we saw that adding a baseline can improve sample efficiency quite significantly, right? So we also saw the reinforce plus baseline approach, where we try to differentiate between returns that are good and bad relatively to our current performance. And we did that by using a baseline value, the state value, to the difference between the G, the sampled value, and some baseline value. And that allowed us to have relative performance. If the relative performance was good, then we'll increase the probability of taking the specific action. If the relative performance was bad, then we'll decrease the action probability, right? And this might not be the case without a baseline. So even if the relative performance was bad, but it will still resulted in a net positive, will still increase the action probability. That's inefficient. Okay, and we saw an example of that, and we saw an example of why this is important. Finally, we used an approximator for both the baseline value and the expected return. This was the advantage actor critique approach, where we computed the relative performance of the current sampled action, but we computed the relative performance both on approximating the capital G value, here in red, and the baseline value, here in blue. And this was the A2C algorithm, right? And later on, by the way, we also saw the A3C algorithm that actually takes a similar approach, but only divides the work between several asynchronous workers for improved performance. And lastly, not seen here, we saw how to maybe extend these approaches to work with continuous action spaces. What next? So next we're going to discuss trust regions approaches. This is exactly what I said earlier when I said that we're going to look at, or when I said that we're actually using a broken version of policy iteration, where we don't wait until convergence for the values and then for the policy, but we run in parallel, which kind of breaks the policy iteration guarantees. But next we're going to discuss trust region methods that allows us to fix some of these guarantees. We'll discuss it later on, while both updating the actor and the critique, not till convergence, right? You'll see how to do that with trust region-based approaches. With respect to assignments, you can now go ahead and start implementing your A2C implementation, reinforce, and deep Q learning. So reinforced and deep Q learning you should have started by now, but you can now start working on the on your A2C implementation. Quizzes, you should be able now, so eligibility traces and deep Q learning you should already be able to, or should hopefully already completed. Now you should be also able now to perform the policy gradient quiz, or should have already started by now actually. And with respect to the project, please start converging on your literature survey. That's it. Anything to add? Okay, thank you.